Hello and welcome to another video. In this problem, we're going to be working on Seat Reservation Manager. And you have a system that manages the reservation state of n seats that are numbered from 1 to n, and you want to implement the class. So the class should initialize a seat manager object that will manage n seats from 1 to n. All seats are initially available, and then reserved fetches the smallest numbered unreserved seat, reserves it, and returns this number. And unreserved a seat with a given seat number. So let's make this a little bit bigger so we can go through the example. So let's walk through our example. So initially we have 5 seats, so we'll just have 5 seats that are available. And there we go. And we want to call reserve. So initially we will reserve seat 1, so we'll kind of maybe like get rid of it or something. So let's just get rid of seat 1. Actually, instead of getting rid of it, let's just circle it. Actually, that's fine. Let's get rid of it. Okay, so we'll get rid of seat 1 and we will return it. Then we'll call reserve, which will reserve seat 2. Then we want to unreserve seat 2. So 2 is now available, so we want to have 2 available now. So that's the smallest one. Then we want to reserve. So seat 2 is the smallest one, so we will reserve it and get rid of it. Then we will reserve again. So seat 3 is the smallest. Then we will reserve again. So seat 4 is the smallest. And we'll reserve again, so seat 5 is the smallest. Then we will unreserve 5, so now the only seat available is 5. Also, it's guaranteed that when you unreserve, the seat will be available, so you don't have to worry about some invalid inputs, which makes this problem really easy. So essentially, all we have to do is have 2 functions, reserve, get smallest number, and pop it from data structure, right? Take it out of data structure. And unreserve, take in number and add it back into data structure. And so now we pretty much have to think like, what's an efficient data structure? And because this problem is kind of easy, I'll talk about it in a little bit more detail. But essentially what we're going to want to use is we're going to want to use a min heap. And so let's write that down. So why a min heap is useful. So a min heap has 3 methods that you need to be concerned with. So it has, first of all, let's describe what a min heap is. So a min heap is a data structure where, I don't even need to go into too much detail, but essentially it's a data structure that lets you get the smallest element in O of 1 time, right? So it's going to be organized in a way, it's going to be an array where the smallest element is going to be at the front, right? So if we have like 5 elements, the smallest element will be here. The rest of it isn't sorted, it's like semi-sorted. And what I mean by that is a min heap is basically a binary tree. So it's a binary tree where every parent is greater than or equal to both children. So let's say we have some children. It's actually, and I'll explain the semi-sorted in a second. Let's make this a little bit bigger. So let's say we have a parent. I think I said it backwards. So min heap, the parent is smaller than children. A max heap, a parent is bigger. So let's say we have a number like 1 here. The children have to be bigger than or equal to 1, otherwise it's invalid. So let's say we have 2 and 5 here. And then same here, this 2 has to be smaller than the children. So let's say it's like 3 and 4. And these have to be also. So you see how it's not like completely balanced. It's not like 1 and then 2 and 3 and then 4, 5. It's not completely sorted, but there is this like thing where every node is smaller than its children at least, right? And it's actually represented in memory with an array. I'm not going to go too far in detail about that. You can look into heap representation. That's like a 30-minute video. So essentially, what it allows us to do is it allows us to get the smallest element in the heap in O of 1 time, because if this is smaller than its 2 children and these are smaller than the children and so on, the smallest element has to be at the top. And so we have 3 operations in a heap that we need to be concerned with. So heapify takes an array and converts to a heap. Right? So you take some numbers, it converts to a heap, and this is O of n time, as opposed to a sort, which is n log n. So it will convert it to a heap. It can be unsorted and so on. So then we also have heap pop, which pops off min element and keeps the rest of the heap in heap form, right? So we're still going to have the same format. So like we'll pop off the 1, and then the 1 will get replaced by some element where it still follows the min heap structure. So let's say we pop off the 1 here, it would get replaced, for example, by like the 2, and then, you know, let's say we have like something like this, right? Like this would be something like this, right? So we'd have 2 here, 3, 4. It wouldn't be exactly like this because there is one more heap property that I forgot to mention. So a heap is a complete binary tree, and what I mean by that is every level is completely full except if there is some level that's not full. Like let's say this level is not full, it's full left to right, which means we can't have a node here without having a node here, right? So it's going to be filled in left to right order. So we might have something like this where these two aren't filled, but we can't like fill the right before the left and so on. And this helps you to know like where the children are located for the under the hood implementation. But essentially, yeah. So let's say you pop off the 1, you might have some representation that maybe looks like this, right? After you pop off the 1. So essentially, that's what a heap pop does. It pops off the min element and keeps the rest of the heap in heap form. This is min element. Whoops. Okay. Now we also have one more operation for heap. Oh, and by the way, so this heap pop is a log n operation. So finally, we have one more thing. So we have the heap push, which adds an element to the heap and maintains heap structure, right? So basically, you don't need to like reheapify a heap when you add one element or pop off an element. It's faster. So this is also O of m log or a log n. And so the nice thing about this operation is, let's say you had some array like this, and to get the smallest element, let's say you would have to sort it, which would be n log n. And let's say I got rid of this number, or whatever. Or actually, instead of that, let's say I added a number. Let's say I added like -5. Well, now with our normal methods without a heap, you'd have to sort it again, and then you'd get the smallest number. And then every time you add or remove, you'd have to sort it again, right? Because you like don't know what you removed or what you added. It could be the smallest. You don't really know where to put it. So to add an element, you might have to add it in the middle of an array, which is also expensive, and so on. Or you might have to get rid from the middle of the array. There's like all these expensive operations. So basically, if you were to just sort it every time, it would be n log n every time times n operations. But for a heap, we now get it down to log n times n operations. So every time we do a heap per heap push, essentially every operation only costs us log n, so we're saving a lot there. So you can think of a heap as like a semi-sorted array where you do have access to the smallest element, but the rest of it isn't necessarily sorted, it's just kind of sorted. And so it's very useful when you are doing, getting the smallest or biggest element, and you're doing insertions and deletions as well. So your data structure is changing. And so basically, coming back to the seats, right? So what we can actually do is pretty easy. Let's say we have 5 seats. So we have these 5 seats. We can make a heap. And then all we have to do is, to get the smallest seat, we can get the front of the heap, or we can do a heap pop. That's log n. You can also access the 0th element of a heap in O of 1 time, because whatever's at index 0 is the smallest element. But we're going to pop anyway. So essentially, to reserve a seat, we can write this down. So reserve heap pop and return. Right? So we do a heap pop, we'll get the smallest element, and we'll return. So let's say we want to reserve the smallest element. So what would happen is we get it's already sorted or semi-sorted. So we have access to the smallest element. So we would pop. Then this would heapify. It would heapify the rest of it, which would be over log n time, right? So a heap pop costs log n time. And to unreserve, we just heap push that element. So that's also a log n operation. So essentially our reserve and unreserve will be log n time, and we can just use a heap to maintain all these things. And we can easily heap hop to get the smallest element for, like, this is basically the perfect use case for a heap. And so that's what we're going to be doing. So let's say we walk through this example, I guess. So if we reserve, unreserve, and so on, right? So let's say we reserve 1 time. So So we will heap pop, we'll pop the 1, then we'll reserve again, so we'll pop the 2. And then let's say we unreserve the 2, we're going to push the 2 back in, and it's going to get pushed in, and the order of the heap is going to be maintained, so the 2 will get pushed back in here. And then if we want to like reserve 2 and reserve 3 and so on, we would just heap pop, heap pop, heap pop, heap pop, and so on, right? So basically reserve is heap pop, unreserve is heap push. And that's pretty much all there is to this problem. So if you know how a heap works, and you know basic heap operations, that's all you need. So let's actually code it up. So now the other thing you want to do is, if you are creating an array and you want to make it a heap, it's faster to first make the array and then heapify, because that's log n, or that's O of n, as opposed to like adding an element one at a time and heap pushing one at a time, because that would be n log n. So what we're going to do is we're just going to create a normal list, and then we're going to heapify it. So we'll say like self.nums equals heapify, and then we can just do a list comprehension here. So I for I and range 1 to n plus 1. So now we'll have all our numbers 1 through 5, let's say. Then we will heapify them to make them in the right order. I don't even know if we actually need to heapify here, actually, now that I'm thinking about it, because I think it's already sorted. So like a sorted array should just be completely fine. So let's actually not even heapify. I think non-heapified would be fine. I'm not entirely sure about this, but let's test it. Okay, so for reserve, we are going to return, and then we're going to need to heap pop here. So heap pop, and for heap pop, you need to give it what you're popping from. So self.nums, and that's pretty much it. And so here, this is guaranteed unreserved. It's guaranteed to be fine. We don't have to check like if this is valid. So what we have to do is we have to heap push, and then we have to say what we're pushing to. So we're pushing self.nums and the number. So seek number. And that's pretty much it. Now, the reason I think this might not work is because there might be some like under the hood thing of how the heap is actually made. Because I think in a lot of languages, the heap is made with like the 0th element being empty and so on. But we'll test it. Either way, we can always add heapify later. It's fine. Let's see. Self.nums. Okay, let's take a look. Okay, it seems to be fine. Yeah, so we don't even need to heapify because a sorted array is already has to follow the properties of a min heap. Because if we draw like, for example, if we have 1, 2, 3, 4, 5, 1 would go here, then 2, then 3, then 4, then 5, and this follows the properties of a min heap. So we don't even need to heapify. And yeah, this is about like a average solution. They're all going to be pretty similar here, so let's talk about all our stuff. So for the time for this init, it's just going to be O of n, right? Because we have to take every number and make an array basically, and then reserve, or the other two functions, reserve and unreserve, are going to be both O of log n, where n is the length of the heap. And you can look into more in detail of how these heap pushes and heap pops work. Essentially, it's basically when you get rid of a number, what you do is you take the last number. So like, let's say I get rid of this. What you do is you take the last number and you put it in. And then from there, you basically try to do as few swaps as possible to make sure this is a min heap, right? So you would swap it with like its smallest child. So you would swap like 2 with a 5 here, 2 with a 5. And then you'd look at the children, you see, are these fine? And these are not fine, so you need to do one more swap here. But that's why it's log n, because you're basically going down like one branch of the tree. Similarly, adding is going to work the same way. You add some big number, and then you swap with its parent if you need to maintain the property of a heap. So that's why the heap pushes and heap pops are faster, while heapify has to do a bunch of these swaps because all the elements are all over the place. So that's roughly that. So time is, yeah, O of n for the initialization, log n for reserve and unreserved, and for space. We can't really have less space than this, right? We have to have some kind of data structure to hold all the numbers. So it's just O of n space. And yeah, I think this is, honestly, if you've seen a heap before, this is basically an easy problem. So definitely not too bad. And yeah, that's going to be all for this video. So hopefully you liked it. And if you did, please like the video and subscribe to our channel. And I will see you in the next one. Thanks for watching.